So let's actually just continue where we left off before we had break. We were just talking about malware, really just talking about different ways of categorizing malware. We talked a little bit about different methods of how one propagates malware, although that's, of course, related to some of our other topics regarding social engineering and the like. We separately looked at the categorization of sort of, the trigger of malware. So you have this malicious software. What is causing it to trigger and actually start the infection process? And we looked at things like particular conditions or just time-based triggers, and why we may want to do that to maybe perhaps make it more difficult to detect whether the malware is being triggered or not, or just to trigger it for particular conditions being met in the case of Stuxnet. And then finally, the third category is that of just the actual payload. Another way to think about payload is, okay, you have this infection that has some sort of propagation, has some sort of trigger where it's time to get going, to start doing the malicious activity. The payload is just referring to, what do we now do? What is the actual bad thing that the malware is doing? Beyond the initial argument that just the infection itself is a malicious activity, you have some unauthorized software running on your system. That is in and of itself something of a malicious act, because you're at the very least you're taking up resources, and even if not that, you're not authorized. You're not supposed to be on that system. Beyond that, what are the things that malware can do? Some of these I think are obvious. I think we know these. Others we haven't really discussed much this semester, and I wanted to make sure we kind of checked all those boxes with regards to this topic. So here's some of the different payload categories. We can start with system and data corruption, meaning like can we corrupt or just destroy the data running on a system. First payload could be to actually do the spreading of malware and not the actual propagation. Next, at some point, potentially in the future, would be to actually destroy some existing data on a system. You may ask, well, why would we want to destroy data? Don't we want to exfiltrate data? Well, you may also want to do that. But in this case, this particular category of payload is actual destruction of the system or of data on the system. There's, of course, lots of examples that do this, although it's considered more sort of, defacing systems than getting any meaningful information off it. You have the Jerusalem virus and its variants. It's a little hard to tell in looking at the assembly source code for it. I provide a link to it from a GitHub deassembling of it and including instructions for how to run it. This would not work in modern Windows or Linux operating system these days. So it's just straight x86 assembly code, where the payload was effectively just to take and monitor every other executable being run in the system. And when that executable was executing, would be to add some arbitrary bytes to the end of it. So in terms of the trigger for that, by default, it was sort of an instantaneous trigger, but it may not have been a noticeable trigger. It was always running, it was resident, it was adding some arbitrary bytes to every executable file once it was running. So the trigger was, in theory, not too subtle, but the actual impact, the ability to measure or detect that something was happening, was itself a bit more of a subtle trigger, in that eventually what would happen, your executables get larger and larger, something's going to happen with resources. You will eventually detect that something is wrong in terms of storage capacity, or just potentially the speed of those executables that are running. It also was a unique at the time that it was also a time bomb that would be set to just pretty much wipe the system whenever it was detected that it was Friday the 13th. It's a very early example of a system or data corruption. That is in comparison to the concept of having a payload that itself is ransomware. We've used the term a couple times already this semester without maybe formally defining it. Again, ware is just the suffix of software, ransom, to hold something ransom. So ransomware is just malware that holds the computer or oftentimes the data resident on that computer hostage. Typically employs a couple of other mechanisms that we'll talk about here to make it very difficult to remove. And at the very least, what it's going to do is going to encrypt the data on those systems that it has infected. Encrypting the data on your systems can, in fact, be a good thing if you're the one in charge of the encryption, if you're the one responsible, if you have access to the decryption key for those systems. The idea behind ransomware is it's this malware that gets propagated in one of many ways, triggered via some mechanism. Once triggered, it performs this disk encryption or particular databases or other files it looks for specifically, makes it very difficult to be removed kind of manually, and provides something of a ransom message saying, if you want to get your data back, provide this amount of money via this mechanism here. So if you provide that ransom, in theory, you get the key, you get your ability to decrypt your hard drives. If not, this can be a very pernicious thing, right? You can potentially restore from a backup, potentially depending on how the ransomware itself is installed on the systems. Oftentimes, the expert advice is to literally start and rebuild entirely from scratch. Basically, rebuild your entire IT infrastructure if you're infected by ransomware. There's different advice you will see out there. I think there's sort of formal U.S. Department of Justice advice or FBI advice saying you're not supposed to pay for the ransom in a ransomware attack. Um, it's sort of an economic, financial consideration more so than probably an ethical one. There's going to be cost associated with removing such a thing, and I guess as an organization, you have to decide if the cost of the ransom is maybe more worthwhile than the cost of having to rebuild everything, plus all the additional downtime that would be associated with that process. This has been more and more in the news lately, just at least locally. It just seems to be happening almost on a monthly basis. The link here is for Mercy, so the main sort of medical system that a lot of you may make use of. Had its ransomware attack that was basically shut down all of their electronic medical records and billing that they were doing. Um, in this example, as far as I can tell, they just did a full rebuild from scratch. You can't always tell in terms of these articles whether or not, or what solution mechanism, how did they actually get past this ransomware attack? Did they pay? Did they rebuild? Did they just sort of back up from existing offsite backups? But it can be very crippling, right? If you are reliant on all these medical records or billing systems and things like that, and if you don't have access to them, it becomes very expensive very quickly for your organization. Um, Early days of ransomware used weak encryption, so it was possible to potentially just break the encryption itself. Nowadays, the examples that are found in the wild tend to be fairly advanced. The same kind of advances that allow for more secure communication in more legitimate means can be equally used to do more secure hard drive encryption as well. You hear, and there's companies that exist to basically provide some sort of ransomware insurance. Um, I'm not really an expert in terms of how those agreements work in practice. I think that'd be a very difficult thing to insure against. Um, but the idea there is that you enter into a contract with a trusted third party. You would probably have to follow some uh, proper security practices, like things like multi-factor authentication, but other auditing or expected software installation to do some real-time auditing of your systems. And then you have insurance. So if that attack happens, they provide some sort of payout, whether it's sufficient to cover or whether it can be used to cover a ransomware payment or not. Um, is not that clear to me. You don't see those details kind of provided in the public, but at least provide some sort of insurance. You get attacked by the ransomware. Once that happens, there is no quick fix for it. But if you have insurance, perhaps there's some legal arrangement that happens at that point, and then you can potentially get some of those losses recovered. There's been a lot of recent examples. This is a more of a national one, the Colonial Pipeline ransomware attack, where there was just the entry point was just via breached employee password. This was a major gas pipeline, and they did pay the ransom, 75 Bitcoin, which was $4.4 million at the time. It's quite a bit more than that now. Um, Mostly had been recovered via sort of law enforcement actions after the fact. But that's an example in which there was the entire gas pipeline was shut down. That becomes very expensive very quickly. $4.4 million may have been a relative bargain for that organization to get rid of the ransomware. And again, even just closer to home, you can find plenty of these articles just in the past couple of years. This was during COVID, so you may or may not have been as hyper aware of it. But DMAC, which was doing primarily online courses at the time, was completely shut down for a full month via a ransomware attack. And for that one, they had to kind of just rebuild their entire IT infrastructure from scratch to kind of avoid that. And that took several weeks for them to do so. And it was all online courses at that point. They really had to shut down all operations at that point. Des Moines Public Schools, also, this was just a year ago, had a ransomware attack. In which there was basically no ability to access student academic records. And then that required effectively shutting down the schools. They couldn't even access phone lines. They couldn't, and the phone lines were needed to open the doors of the building. So it sounds like you could still teach school even with no computer access, but in this day and age, apparently you can't. They had to extend the school year. They had to also effectively rebuild everything, in this case, from offsite backups here. So ransomware is not just a theoretical thing, right? I mean, so it is a piece of malware that gets propagated one way, shape, or form, and effectively it's either looking for particular databases, other well-known important files, or just effectively full drive encryption using modern cryptographic methods. It's called ransomware because the whole point of that isn't really to shut down the organization permanently. It is to ransom their storage, right? Their files and databases and the like. And say, pay us a certain amount of money, we will restore these things. Sometimes there's a little bit of an information asymmetry there. It's not clear, for example, how much funds Des Moines Public Schools would have even had to pay a ransomware attack. Are they allowed to pay for that via their, funding mechanisms? How much is the right amount for an organization's storage and student records or medical records? It's not that clear to me how these negotiations ultimately happen at the end of the day, but we do have some real examples in which actual ransoms were paid. It is still considered a very effective and real attack that one has to watch out for. So that's ransomware. There's also just separately just data or information theft, where the malware's point, the whole purpose of it is to gather some data and to then exfiltrate that data. It could be then used to stage subsequent attacks. It could be, grabbing username and password and authentication credentials to log into banking or other just systems in general to be able to further impersonate targeted users. Or it could be specific, corporate company secrets, government secrets that are being stolen via the malware itself. This is from the Mitra attack database, just one example of I can call it a hacking group called Dark Hotel, and they were pretty notorious for targeting company executives. This was in South Korea through business hotel Wi-Fi networks. That CEO type would go to the hotel or hotel chain, would connect to the network there, and that would be kind of the target point, the propagation of the malware onto those systems, just to directly steal and snoop the login info that they would be using when connected to those networks. That website we hadn't looked at yet this semester. I had very briefly talked about Mitra and the attack framework, which just itself is another way to kind of categorize the kind of attack methodologies and software weaknesses and the other things we've talked about via other resources. They also have an attempt to enumerate the well-known, mostly international, call them darknet groups or just hacking groups, those who are involved in cybercrime largely. So that's worth a check at some point. This is just the Dark Hotel, just an example of a group that has been known to steal information, but all of these groups are doing some sort of nefarious things here. It's kind of fun just to see all the great names. They have really good naming schemes for these various groups. I haven't really clicked on any of them to know, for the most part, some of them are more well-known than others. There's a lot of North Korean groups, there's Russian groups, there's groups based in the US as well. And if you have some time, you can click on that link on the slide and just look at some of the various groups and see what they've been up to historically or even still active today. What kind of malicious software, what kind of things are actually available in the wild. We won't do that today, though. Other things that can enable information theft is software or hardware that is doing key logging. We heard the term key logger before. We haven't used it in labs this semester. When we talked about physical access and how the game is effectively up, we looked at just what can be provided via USB device that could act as a keyboard. But beyond that, one could actually just be capturing the keystrokes themselves. That same piece of hardware we played around with could have done exactly that as well. But a keylogger doesn't need to be hardware. I think historically it wasn't. It was a software mechanism for sort of just capturing every keyboard event, storing that information, sending that information. You can imagine that if you had a keylogger installed maliciously on your own system, they'd have access to effectively everything, right? Every message you've ever sent, every authentication you've done that involves typing in a password would have then been monitored, stored, eventually sent out. But it can also be could be a hardware mechanism as well. This is one of many such pieces of hardware one can purchase. Um, Key grabber USB, and kind of look at what it does here. That's actually larger than I would think an equivalent device would need to be. You need some sort of storage on there if it's just going to be storing it in an offline mechanism. You probably don't need that much storage. I was looking at this example that says there's a keystroke recorder that has up to 16 gigabytes of memory to store keystrokes. But just some of my own kind of quick mental math, that's a lot of keystrokes. If you assume for the most part each keystroke is just a single byte, so 16 billion keystrokes, um, you can just think about a typical day for yourself. Even maybe a typical day sitting in an office in front of a computer, your keystrokes is probably measured in the upper hundreds, low thousands, and so this would be potentially many, many years of key logging data, hundreds and thousands of years of key logging data, but it's maybe more than what's necessary. So it's a little too intrusive looking for me, right? It looks like it'd be obvious if you had such a thing plugged in. It wouldn't work it could work in a laptop with an external keyboard. It's probably more likely to be used for a workstation type form factor. And I guess if the keyboard's just plugged in somewhere arbitrarily underneath your desk, you don't really think about that connection at all. And so maybe it can be installed somewhat unobtrusively there. The idea is it's just monitoring every single keystroke. At some point, having some mechanism by which it can generate that report so that someone can then go ahead and access that file, that information after it's been stored. This one looks like it's just storing it locally. One could imagine other ones that also maybe have Wi-Fi or other capabilities. I'm trying to look at the documentation for this one. Yes, you plug it in. We can figure that out. Has a special key combination that causes it then to open up as a device and share sort of a text file of all the things that have actually been stored on it. In this case, I'm sure you can change it, but if you press the S, B, and K keys simultaneously, it detects that and changes itself to become a flash drive where you can see what was previously been stored on that device. I don't know if that's a good enough key combination. I guess I would never type S, K, and B at the same time. Maybe that's why they came up with it. Maybe it means saved keyboard or stored keyboard. I don't know. Maybe that's all it means. You'd think you'd want to have something that would never accidentally be triggered if one really wanted to use it for nefarious purposes. So maybe it can be customized. Certain keyboards can only do so many simultaneous keystrokes in the first place anyway. There may be some more safe way to do it than just hoping that the user never types those three keys at the same time. That is a key logger. That's a physical key logger. There's no reason it has to be something physical. That's something that can be installed without any sort of software, any malware being installed, but it can be entirely just a software device as well. That the keyboard device itself, the software that is generating those characters, that is intercepting those signals coming from the physical keyboard itself, can be exploited to then store that information, send off that information. It's not exactly the same when we were talking about data exfiltration, but a similar term that we hear used is referred to as spyware. A keylogger is, in a sense, a type of spyware because it's capturing user activity. But I think that term has become more of sort of an umbrella term referring to capturing specific types of user activity. Keystrokes are also user activity, but if, for example, we only wanted to capture when the user went to their banking website and we wanted to detect exactly what was happening on the banking website, that could be possible via a keylogger and some very careful filter, but you could also have special software, more broadly referred to as spyware, that would be looking to capture that direct type of user activity. That could be via, again, the kind of things we've talked about with malicious websites, doing man in the middle with regards to the networking connection, where you're actually presenting a malicious version of the website. That is what we're referring to when we talk about spyware. The NSO group is pretty notorious for the development of the Pegasus spyware. I was looking for them on this list, the Pegasus group. They're not considered a sort of a malicious, private, or state acting group. I guess it really depends on one's perspective. They're referred to in Wikipedia as an Israeli cyber intelligence firm, primarily known for the proprietary spyware Pegasus. What Pegasus is best known for, they've done a couple other things as well, is when you have a lockdown Android or iPhone, being able to unlock it for you, or to install spyware ahead of the time to say, capture this particular activity happening on this particular device. It is interesting. So they are not categorized. They're not considered a malicious hacking enterprise. The argument against it, just looking at their own website and also reading the Wikipedia article, is I guess they primarily contract with state agencies. So I guess if you're working primarily with law enforcement actions and with contracting with particular governmental agencies, then I guess you're a more legitimate enterprise. But it's not so different from what some of these other companies are also doing. These organizations are also doing. Um, it's it's a pretty impressive website, and I would happen to say that some of you have been talking to me about trying to find summer internships and jobs in the field, and hiring is a little tight right now. Things are booming at the NSO group, so you may want to take a look at their website offline. Um, let's see what kind of things they need. Researcher sounds legitimate. I guess you could be a bookkeeper as well. Um, what do they require to be a researcher? You just have to upload the resume. We should do this as a class project. Incredible benefits, hybrid and flexible. Sounds excellent. I don't know. Work with top-notch researchers, but what do they require? BS in computer science or equivalent. Many of you are well on your way, if not reaching that goal. Relevant military experience. I don't know. That would be a limiting thing. Knowledge of mobile device internals, Linux kernel, Windows internals. Well, some of you, if you're taking operating systems classes, taking ComSci 252, maybe CPRE 308, maybe the reverse engineering class as well. Well, it looks like they're hiring. So that's all I noticed, that they're not on this list. They're considered quite legitimate. And not only are they legitimate, they're hiring. So those of you who are looking for jobs, I found you a new lead that I didn't realize was available here. Still spyware. It's still software that's being installed on a device that's meaning to extract information. I guess if it's done under the aegis of like a legitimate warrant, then I guess it's not a malicious software. Still malicious to the user, but we don't think of it as a whole as being an evil, unethical kind of activity when there's some state government associated with it or federal government associated with that action. Other types of covert access, the terms that are used, I think, incorrectly interchangeably is backdoor and trapdoor, both referring to a secret entry point into a system. To me, a backdoor is a secret entry point. You have a front door, that's the primary entry point. You have a backdoor, that's the secret entry point. To me, a trapdoor is maybe a secret exit point. But I guess you can also enter through a trapdoor. In The Simpsons, at least, there is a big difference between a trapdoor and a backdoor. In the first one, that is a trapdoor. He presses the button and he escapes and he leaves. In a backdoor, you have potentially the very, very secure front door mechanisms where it's very difficult to access one particular resource. You may not be old enough to know exactly what happens at the very end of this. And then there's just like an open mesh fence at the end of it where a dog has already come in. So that's a backdoor. That one is a trapdoor. At least on The Simpsons, they're two different things. The type of mechanism we have used and played around with all semester, via malware at least, is that of the reverse shell, right? So you have your malware. Its actual malicious activity is just to create that backdoor or trapdoor, that secret entry point into the system that usually there's some further point. I mean, we usually stop in this class at getting and reaching a reverse shell because that's what we need. We've shown we have access. We can access what we need to access. Presumably, you do that to have a more persistent presence on the device, on the system, so that one can do other things like destroying data, leaking information, and the like. It doesn't have to be a reverse shell. It could be via some just sort of hard-coded way of accessing the system that is just built into the system. That was that paper we talked about before break, the Reflections on Trusting Trust paper, where he was basically building a backdoor into all of the login software to be able to provide a separate set of credentials to be able to remotely access and potentially help with administration of remotely accessible systems in the early days of Unix. The other term you will hear, and it is related to providing that backdoor / trapdoor access, is the rootkit. So kit just means a mechanism for deploying additional software. Root is how we've been using it, right? Having sort of super user abilities on a system. So rootkit is a piece of software or a series of software packages that allow you to create additional software that eventually is installed on the system to provide that persistent root access. Typically, there's some other vulnerability in the first place for all of these things, right? So we have the malware propagation. There was some mechanism by which malware can be installed on a system. Then there's the trigger via some mechanism, whether it waits a while, whether it's right away, whether it's based on certain conditions that it detects, it actually triggers and says, let's do the malicious thing at that point. And then you have the actual activity, the actual payload itself. In this case, the rootkit is itself a secondary payload that can be used to then stay resident on the machine, be very difficult to detect, and potentially do other things like even installing ransomware or exfiltrating information from the machine. What separates rootkits from some of these other malwares, although other malware may have other mechanisms to attempt to sort of elide detection to be harder to detect than usual, the trigger mechanism via other sort of simple hiding mechanisms as well. What usually is considered a rootkit is that the hiding mechanism is first and foremost the initial goal of that piece of software. If it doesn't do anything like overriding existing system calls to make it more difficult to detect that it's there, then it's still malicious. It still can do all these things. It still can be persistent. It usually doesn't fall into that bucket of rootkit here. So you have existing mechanisms that would allow you to detect what software is currently running on my system. In user space, you can run the ps command to see what processes are currently listing here, ls to list what directories or what files or directories are currently available to me in the system. Historically, at least in the very early days of rootkit, it would be a piece of user software that would attempt to modify utility programs to just hide its own presence, its own existence. So kind of like that Reflections on Trusting Trust paper, although he was talking about the compilers in the first place, but modifying the login command to allow for sort of a malicious version of login. The rootkit, at least in the early days, would do things like, let's modify the ls command. If you modify the ls command such that it acts exactly as the intended ls command, except it always doesn't show this one particular file that happens to be on the system, that is one mechanism to hide that this software is available. Or to modify the ps command, which allows you to view all the various processes currently executing, to act as the regular ps command, except to not show that this particular rootkit process is itself running. That's what usually distinguishes a rootkit from just any other type of resident software here. It's attempting to hide. It's overriding, modifying existing monitoring, auditing mechanisms to be a little bit better at hiding. There's a pretty famous case in the early 2000s, back when we had CDs to listen to our music, in which Sony was very concerned about music piracy. They were very concerned that, this may sound really old, but we would go to the store, we would purchase a CD. We would also have very early sort of MP3 players. You're looking at me like I'm crazy here. So one of the first things you would do is you'd have a CD player in your computer, you'd put in the CD, you would rip all the files off that CD so that you could take your music on the go, even back then. Or share them via peer-to-peer and other file sharing mechanisms to people who have not yet purchased the CD. That was a very big deal at the time in pre-streaming, pre-legitimate, online sharing of music days. And Sony thought, well, we don't want our users to be able to do that. So when they put the CD into a regular audio player, it'll act as a regular CD. When we put the CD into a user's computer, it'll just install a small piece of software that will make it more difficult to actually install other software that would then rip those files off the CD to make the step at least somewhat more difficult for those to be able to do that. It did so by installing a piece of software that always maintained and stayed resident on the software, that would, every time you even tried to delete that and uninstall that software, it would have a hook to kind of reinstall itself after the fact. That is arguably at least a rootkit. Intention also matters here, but it was a piece of software that was installed via some propagation. So it was a physical propagation. It had some trigger once you were trying to install one of these other pieces of software, and it had at least some sort of malicious payload, which is being very difficult to uninstall after it was initially installed here. And they got in some modest amount of trouble for that at the time. A little bit of an arms race with regards to rootkits in terms of who is doing the installing and who can monitor and react to that installation. You can kind of guess where that's going. If it's a piece of user mode software, user level permissions, then a kernel module could then detect that those changes had happened. You could have a more trusted boot process that would detect if things like the ls and ps commands themselves have been modified. The reason that's an arms race is there's not necessarily a reason that a rootkit has to be running at a user level. It could then run itself in kernel mode. You'd have a kernel level or kernel mode rootkit, which would actually make the changes within the operating system kernel, the core routines that are allowing you to have all these other user space applications. If you modify that, then you have a little bit of a reflections on trusting trust problem again with who is monitoring that this modification is happening, if you're in fact changing the software that is checking the monitoring itself. Most kernel rootkits would modify some of the basic system calls. If you haven't taken an operating systems class yet, you may not be that familiar with systems calls, but you've done some programming that you know you need to have an ability to open a file, to read a file, to write to a file. Those are provided some medium to higher level APIs to you as the programmer. At the end of the day, the implementation for all of them is roughly similar because they're relying on the underlying operating system kernel to provide a mechanism to open a file, to read to a file, to write to a file. That is a syscall, a system call, calling into the operating system, and there's a syscall table. So there's just a number of these things, and they're standardized across various operating systems and versions of operating systems that says, I would like to open a file. That's going to be syscall number 2. And it's ultimately kind of an assembly level thing that happens here. These are not secret information. These are well established mechanisms here, that there's a syscall instruction. The operating system kernel takes over. It actually monitors a value placed as an argument to that syscall function, and it's going to do various kernel things based on what value is provided. So there's a table of these things. There's a table, and then the kernel themselves has a set of effectively assembly instructions associated with each of these entries in the kernel table, such that those of you who've done C programming, you are calling fopen to open a file, or cin or other mechanisms in other languages to open a file. That code is actually not doing all that much. It's doing some quick permissions checking and the like. It is calling the lower level call, which is just referred to as open, which is calling the syscall sysopen. And the real functionality takes place in that kernel module, which is why you write in different programming languages. At the end of the day, the way you're accessing your system is going to be roughly similar, no matter what is happening. Every time you have a programming language, whether you are manually allocating and managing memory yourself, or whether you're reliant on more dynamically allocated and restructured data structures to do that for you, someone under the hood is calling mmap. Someone's doing memory mapping and giving you a block of data to play around with at that point underneath the hood. So doubling back to this idea of a kernel rootkit is you have these system calls, they're stored in a table, and you have this table that maintains that mapping from entry number 2 to what blob of code corresponds to entry number 2. What a kernel level rootkit would then potentially be able to do would be to say, let's keep all those numbers, let's keep all those tables, let's just modify what happens when number 2 gets called, when number 17 gets called here. And so if you were to look at the source code of a kernel level rootkit, it's not so different from sort of low-level operating systems programming that you may have done in other courses. So diamorphine is just one example, actually, of many. See if I can zoom in here a little bit. As always, when we look at these examples, the goal is not that necessarily you can look at that and instantly know exactly step by step what it's doing. This example, though, it is written in, we'll call it Linuxy kernel style C. But those of you who've done that, who've taken an operating system course, it's definitely not outside your ability today to kind of look at and understand what it's doing here. But that's exactly all that it is doing. You have to kind of squint at it or take my word for it. Either one is fine. But it's looking to find where in the syscall table is the system call to kill a process. Why would a rootkit want to know that one? And the reason it has to look it up is depending on what version of the kernel you're using, it could have changed. But it's going to return back 62, and whatever entry point is there is a syscall 62. We talked about ls and ps commands. That's a useful thing potentially for a rootkit to care about. Why would it care about the kill system call? So it can't be killed. Looks for it. That is, I'll have to kind of track through where this happened. That's basically a function pointer saying, effectively, where in the kernel, when it's time to kill a process, what actual blob of code is it executing and where is it located? So it's a function pointer to that system call. And then the idea is, let's in fact override it with our own version. Also just a function pointer. Grab the current kill function, because we still probably need that one to work. Overwrite that table with our so-called hacked kill here. This is more for proof of concept than anything. And we can see, probably should be able to find in here, what is actually happening in hacked kill. And it is written that sort of kernel-y kind of mode that's a little bit hard to understand here. But for now, consider this just a function declaration. Take some input registers as input that does probably different various things. There's different flags you pass to the kill command. And in this case, it is checking which signal. It is creating a new signal to check if I want to make a process invisible or not. Checks for the task that we're looking to potentially kill and kind of flips the flag as to whether or not it is invisible or visible to the regular kill command or not. So just a mechanism by which you pass it a certain, whatever this signal would be defined as. See if I can find the actual, I can't see the definition for it in this file, it may be in the header file. But given that signal, I'm sure it says there in the documentation somewhere what that actual value would be, just an integer value as well. Hide that particular task. And then make sure you call the original kill function itself after the fact. So that's all a rootkit is really doing. Whether it was in user space where I'm just trying to overwrite an existing user space utility, or we go one level deeper and say, let's modify actually what the kernel is going to do when it gets a command to kill a process. The idea is to kind of hide that it exists. To hide that it exists by overriding those kind of kernel functions that would be used to monitor, destroy, delete processes that are executing. But it is kind of a continuing arms race, right? So that's at the kernel level. You can certainly go further as well, right? What if I'm just running my OS on a virtual platform, virtual machine? You could then have a rootkit that potentially at least would take over the hypervisor itself, right? So for every layer of software abstraction one wants to add, in theory, the rootkit just has to go one layer below that to be able to preserve its own access on the system. The argument for why, it's an arms race, but the argument for why it's potentially a winnable arms race is, the amount of vulnerabilities in user space is massive, right? In terms of ways we can find entry points to overwrite ls or ps command. There's just lots of them. We find them every day, right? then the subset of things that we can take advantage of to overwrite things in the kernel is going to be less than that. It's more strictly audited code. It's a smaller amount of total code as well. That's not to say we don't have kernel exploits. It's usually a big deal when one is discovered, but they are discovered. And then if you take it further than that, a hypervisor, it tends to be a very small, we'll say relatively small, very heavily audited, sometimes even formally verified piece of software, where the hope is that there should be less likely to be a vulnerability at that level that could be taken advantage of. But in that sense, it is still just an arms race, where the entry point needs to be 1 point lower than the current level of monitoring software, such that it makes it very difficult to detect what is happening in that particular system. And finally, we can talk about in terms of the different attack agents that are possible in terms of this payload. Um, the idea that is that you are taking over the computer via some reverse shell, via some rootkit, via some other trigger and mechanism that we have here, and then you are then using the computational resource that vulnerable exploited computer is providing you to go now do something else. We talked about other botnets in the past, and oftentimes botnets are used to just provide very effective distributed denial of service. That's still an active use for them. If I really want to shut down this network service, if I have 100 computers, it's a very difficult thing to do. If I have 100,000 computers, it's a relatively more feasible thing. And then there's also kind of a recursive thing where we take advantage of these computers, we exploit them, we then use them to discover other computers that could be exploited. So it's exploiting for the sake of growing this network. But we've used the term bots, but also you'll see the term zombies or drones. These are just computers that have been taken over that can now be used to do some other malicious thing after the fact. The real differentiator there, and certainly when we talk about botnets, that's what makes it different from a standalone piece of malicious software or even a worm itself, is that there tends to be some sort of remote control aspect to it. When we have a reverse shell, that is a form of remote control, but it's not really a scalable one necessarily. When you have a botnet, by contrast, you have presumably many more of these exploited machines, whether it's IoT devices or traditional computing systems as well, and you have some mechanism to, in a scalable way, command and control to tell them what to do next, to provide the next set of instructions for what they need to do. Doesn't need to be continuous. I don't need to be logged into a remote shell to be able to tell this malware what to do next. They are designed to periodically check for what their next command needs to be. That then allows these botnets to be effectively provided as a service as well, right? We have that many orange and blue bots in the diagram here. You could have one sort of global bot master here, or you could have someone who controls all these, but then sells access to one subset or a particular number of command and control servers to say, okay, for this price, you take advantage of this many bots to create what havoc you want to create here. And there's lots of different ways that command and control has been implemented in the past, very early days, and apparently still today, which was a little surprising to me. Bots would join Internet Relay Chat, IRC channel. Also probably a little bit before your time, but kind of the original live internet chat. In many ways, superior to Discord and the like today. But it was sort of the original kind of way that via networking you could communicate with other people in a somewhat scalable mechanism here. The idea is that there'd be a particular IRC relay, IRC server that would be used to then provide a series of commands. To someone who just happened to be looking at the channel, it would either be some sort of obfuscated code words or just kind of random garbage that was being sent to it. Still apparently occasionally in use, but can be relatively easy to detect when that's happening because it has a particular network protocol that it uses that can be detected if that's happening and can be then potentially shut down. But ultimately, any service that provides an API can be used as command and control. So these are just a few examples that I found. You can find many, many others. One that I thought was interesting is because there's an API for this, a botnet that used Gmail drafts as its command and control here. The idea that you create a message in a Gmail account, and you don't actually send it to anyone, that could maybe more easily detected. You just save it in drafts form, and these bots know to go connect to that account and check to see what the status of that draft message is. Also could be used for Google Docs as well, right? Anything that has an API for programmatically both writing to as well as reading from also probably needs some sort of authentication or permission structure associated with that as well, would allow for that. So via use of email, social media, at least for a time when the APIs were a bit more open than they are today, was in common use for sending those command and control messages. You have just a random Twitter account or a network of Twitter accounts, and you send these direct messages, or you just post publicly available garbage to that Twitter account, and it wouldn't be that obvious that such a thing was actually a series of botnet command and control messages, because to at least a user just kind of perusing it randomly, it would just look like garbage, just look like junk. And there's lots of theories about that. To what extent is the amount of network traffic on social media sites, is it actually legitimate traffic? How much of it is auto-generated? How much of it is AI? How much of it is driven by things like botnets? But it turns out, I think it'd be fair to say, and you can read this article offline, you can think of your Instagram, your Facebook, Twitter, things like that. If you have an API for posting and certainly for reading, you can have a command and control service from that. The trade-off is how straightforward it is to set up, how scalable it is, and then how easy it is to detect, and once detected, how easy it is to shut down. Another example is the idea of DNS fast fluxing, so that you have many IP addresses associated with a particular DNS entry, which is appropriate for like load balancing and the like, where you maybe do some sort of round robin or other kind of scheduling where you say, when I go to istate.edu, sometimes it's this IP address, sometimes it's this other IP address, sometimes it's one of these 100 IP addresses, so I can kind of physically load balance the site. That can also be updated to be served as command and control networks. DNS can be taken down by a centralized authority, but not all DNS authorities will be quick to take things down. You see a lot of these examples being used elsewhere where detection is difficult. It is just one other message in a large stream of just presumably garbage-looking messages that are out there, and can be very effective for botnet command and control. Let's leave things here for today. Come back on Thursday, of course. We'll have our final micro quiz of the semester, and then our sort of final last optional topic this semester. We'll start talking a little bit more about wireless security. Thanks.